Hi, my name is Jason Shoemaker. I'm an assistant professor in the Department of Chemical Engineering at the University of Pittsburgh. And my research team primarily focuses on using computational modeling to understand how we can improve treatment of respiratory infection. This is the idea of trying to basically develop very small computational models of the individual pieces of your immune system and putting those pieces together to understand how do they interact with each other. And if you applied a drug or some kind of other treatment, how does that go ahead and impact then the overall immune response? And this is an important area right now because you've probably heard from the multiple studies and multiple news headlines associated with COVID-19 that your immunity tends to be a major player in determining whether you have a severe or mild outcome. And a lot of times it's actually pretty unintuitive what those results can be, where very often someone that has a relatively healthy immune system, but sometimes maybe experiences too strong of immune response, actually has a more negative outcome. So it's not as simple as trying to make a very strong immune response or a very weak immune response, where we really have to try to find something in the middle and basically tune your immunity to ensure that you're having a better outcome in the end. Agent-based modeling is a modeling that's actually been around for quite a long time, especially in the field of epidemiology, but it's becoming much more popular now in other fields such as chemical engineering, which is my field. And the premise there is that you want to try to build things really from the ground up, almost like you do with a video game, where within a video game you have a character and you give that character particular properties and particular abilities to move around the screen and or engage other people in their environment. And we do the same thing then with the different cells that make up your immune response. So we say your B cells can do this, it can sense these kind of cells, your T cells do this, and they train over time. And we basically just give them all the different rules that immunologists have been discovering over the last 100 years to try to let them behave as the individual components of your immune system. And then once you have all those rules kind of laid out in each one of the agents on each one of your immune cells, then you just let them interact and work together to see what happens long term. Does it lead to a healthy clearing of the viral infection? Or does something negative happen where maybe it starts going in the wrong direction? It starts causing a lot of inflammatory action to occur where you get lots and lots of immune cell buildup within your tissue. So by having a model that can try to capture these different dynamics, we can really dive in deeply and try to explore how do these dynamics, how are they regulated? And then if we understand how they're regulated, maybe we can regulate them even better. The real world application is what we want to do ultimately is improve human health. We want to find a way to really optimize your immunity. So we want to try to find ways of what is the optimal time to give you a particular drug, if there's certain even dietary changes that we could do to actually improve your health outcomes. We really just want to get to the point where we could really help engineer and improve your individual immune response for general respiratory infection, whether it be COVID-19, influenza infection, RSV virus. We're really interested in trying to apply this generically across all respiratory infection.